hypothesis of an induction motor breakdown leading to the escalator malfunction is plausible. When induction motors are overloaded, they can exhibit several behaviors. Firstly, they can stall, where the motor slows down and eventually stops. Secondly, slip can occur, where the motor slows down but continues running, increasing slip between the stator and rotor. Thirdly, overheating can happen, where the motor draws excessive current, causing it to overheat and potentially trip a circuit breaker or safety switch. Fourthly, in rare cases, the magnetic field in the motor can collapse, causing the motor to lose speed control and freewheel. The following sequence of events might have occurred at Coors Field. 1. The escalator was heavily loaded beyond its design capacity. 2. The motor initially tried to maintain constant speed but began to slip due to a high load. 3. The load exceeded the motor's ability to maintain speed, and the induction broke. 4. With no speed control, the motor accelerated rapidly, causing the escalator to speed up and dump the passengers. Other factors may have also contributed to the incident. The escalator's speed governor is designed to prevent overspeeding. If it malfunctioned, it could have failed to limit the escalator's speed. Although initial investigations did not reveal any broken gears or transmission parts, there could have been a subtle mechanical failure that contributed to the malfunction. An electrical fault, such as a short circuit or a loose connection, could have caused the motor to behave abnormally. A thorough investigation is necessary to determine the exact cause of the incident. This will likely involve detailed examination of the escalator's mechanical and electrical components, as well as a review of the maintenance and inspection records. The hypothesis that the induction motor broke down and caused the escalator to freewheel is a plausible explanation for the incident at Coors Field. However, other factors may have also played a role, and a comprehensive investigation is needed to identify the exact cause. Induction motors, commonly used in various applications including escalators, operate on the principle of electromagnetic induction. These motors consist of two main parts, the stator and the rotor. The stator is the stationary part of the motor and contains windings that create a rotating magnetic field when alternating current is applied. The rotor is the rotating part of the motor and is typically a square cage rotor, which consists of conductive bars embedded in a laminated core. When the rotating magnetic field produced by the stator sweeps across the rotor conductors, it induces a current in the rotor. This induced current creates its own magnetic field, which interacts with the stator's magnetic field, producing torque and causing the rotor to rotate. Induction motors are designed to operate at a synchronous speed, which is determined by the frequency of the alternating current supply and the number of poles in the motor. However, under normal operating conditions, the rotor speed is slightly less than the synchronous speed. This difference in speed is known as slip and is necessary for the motor to produce torque. As the load and the motor increases, the slip also increases, causing the motor to slow down slightly. However, the motor is typically able to maintain a relatively constant speed until it reaches a certain overload threshold. When an induction motor is overloaded, it can exhibit several different behaviors depending on the severity of the overload and the design of the motor. One possible behavior is stalling, where the motor slows down and eventually stops running. This occurs when the load in the motor is so high that it exceeds the motor's ability to produce torque. The motor's magnetic field weakens, and the rotor is no longer able to rotate. Another possible behavior is slip, where the motor slows down but continues running. This occurs when the load on the motor is high, but not high enough to cause it to stall. The motor's slip increases, and the rotor speed decreases, but the motor is still able to produce some torque. Overheating is another potential consequence of overloading an induction motor. When the motor is overloaded, it draws excessive current from the power supply. This excessive current can cause the motor windings to overheat, which can damage the insulation and lead to motor failure. To protect against overheating, induction motors are often equipped with thermal overload protection devices such as circuit breakers or thermal relays. These devices are designed to trip and disconnect the motor from the power supply if the motor's temperature exceeds a certain limit. In rare cases, an induction motor can experience a breakdown of its magnetic field, leading to a loss of speed control and freewheeling. This can occur if the motor is subjected to a sudden and severe overload or if there is a fault in a motor's electrical components. When the magnetic field collapses, the motor loses its ability to produce torque, and the rotor is free to rotate at whatever speed is dictated by the load. In the case of the Coors Field escalator, it's possible that the escalator was heavily loaded beyond its design capacity. This could have caused the motor to initially try to maintain a constant speed, but it began to slip due to the high load. If the load exceeded the motor's ability to maintain speed, the induction could have broken, leading to a loss of speed control and freewheeling. With no speed control, the motor could have accelerated rapidly, causing the escalator to speed up and dump the passengers at the bottom. However, it's important to note that other factors may have also played a role in the incident. The escalator's speed governor is designed to prevent overspeeding. If it malfunctioned, it could have failed to limit the escalator's speed. Although initial investigations did not reveal any broken gears or transmission parts, it's possible that there could have been a subtle mechanical failure that contributed to the malfunction. An electrical fault, such as a short circuit or a loose connection, could have also caused the motor to behave abnormally. A thorough investigation is necessary to determine the exact cause of the incident. This will likely involve detailed examination of the escalator's mechanical and electrical components, as well as a review of the maintenance and inspection records. The investigation should also consider the escalator's design capacity and the actual load that was present in the escalator at the time of the incident. To prevent similar incidents from occurring in the future, it's important to ensure that escalators are properly maintained and inspected on a regular basis. Escalators should also be equipped with appropriate safety devices, such as speed governors and overload protection devices. Additionally, escalator users should be aware of the weight limits and other safety precautions to avoid overloading the escalator. Induction motors are generally robust and reliable machines, but they are not immune to failure. Overloading, overheating, and electrical faults can all cause induction motors to malfunction. Regular maintenance and inspection can help to prevent these problems and ensure that induction motors operate safely and reliably. Furthermore, understanding the principles of induction motor operation and the potential consequences of overloading can help to prevent accidents and injuries. In addition to the factors already mentioned, there are several other considerations that could be relevant to the Coors Field escalator incident. Firstly, the age and condition of the escalator could have played a role. Escalators are subject to wear and tear over time, and older escalators may be more prone to mechanical or electrical failures. Secondly, the maintenance history of the escalator could be relevant. If the escalator had not been properly maintained, it may have been more likely to malfunction. Thirdly, the design of the escalator could have contributed to the incident. Some escalators are designed with a steeper incline or a higher speed than others, which could make them more dangerous if they malfunction. Fourthly, the training and experience of the escalator operators could be relevant. If the operators were not properly trained, they may not have been able to respond appropriately to the emergency situation. Fifthly, the presence of any safety features on the escalator, such as emergency stop buttons or handrails, could have affected the outcome of the incident. If these safety features were not functioning properly or were not easily accessible, it may have been more difficult for people to stop the escalator or to avoid injury. Finally, the environmental conditions at the time of the incident could have played a role. For example, if the escalator was wet or slippery, it may have been more difficult for people to maintain their balance. To conduct a thorough investigation of the Coors Field escalator incident, it would be necessary to gather information from a variety of sources, including eyewitnesses, escalator maintenance records, and escalator design specifications. It would also be necessary to consult with experts in escalator safety and engineering. The goal of the investigation should be to determine the exact cause of the incident and to identify any steps that can be taken to prevent similar incidents from occurring in the future. These steps could include improving escalator maintenance procedures, upgrading escalator safety features, and providing better training for escalator operators. In addition to the technical aspects of the investigation, it would also be important to consider the human factors involved in the incident. This could include examining the actions of the escalator operators and the reactions of the people who were injured. The information gathered from these sources could be used to develop recommendations for improving escalator safety and preventing future injuries. Ultimately, the goal of the investigation should be to ensure that escalators are as safe as possible for the people who use them. Escalators are an important part of modern transportation systems, and it is essential to take all necessary steps to prevent accidents and injuries. By conducting thorough investigations of escalator incidents and implementing appropriate safety measures, it is possible to create a safer environment for everyone. The analysis of the escalator incident at Coors Field necessitates a multifaceted approach, integrating engineering principles, safety regulations, and operational protocols. One critical aspect to examine is the motor's torque speed characteristics under varying load conditions. Induction motors, while generally maintaining a consistent speed, experience a reduction in speed as the load increases. This phenomenon, known as slip, is inherent to their design. The amount of slip is proportional to the load. As the load increases, the slip increases, and the motor speed decreases. However, this relationship is not linear. There is a point beyond which the motor's torque production capability diminishes rapidly, leading to a stall condition. The question then becomes whether the escalator's motor was operating near this critical point when the incident occurred. If the escalator was already heavily loaded, a sudden increase in weight could have pushed the motor into a region where it could no longer maintain sufficient torque, leading to a rapid deceleration or even a brief stall. The subsequent release of the load, either through passengers falling or the escalator reaching the bottom, could have resulted in a sudden surge in speed as the motor attempted to return to its normal operating point. Furthermore, the design and functionality of the escalator's speed governor are paramount. A speed governor is a safety device designed to prevent an escalator from exceeding a predetermined safe speed. It typically consists of a centrifugal mechanism that activates a brake system when the escalator's speed surpasses the set limit. The effectiveness of the speed governor depends on its proper calibration, maintenance, and responsiveness. If the speed governor was not properly calibrated, it may not have activated at the correct speed. If it was not well maintained, its mechanical components may have been sluggish or prone to failure. And if it was not responsive enough, it may not have been able to halt the escalator's acceleration quickly enough to prevent the incident. The braking system itself is also a critical component. Escalator braking systems typically employ a combination of mechanical and electrical brakes. Mechanical brakes provide immediate stopping power, while electrical brakes offer smoother deceleration. The interplay between these two braking systems must be carefully coordinated to ensure both safety and passenger comfort. If the mechanical brakes were not properly adjusted, they may have engaged too abruptly, causing passengers to lose their balance. If the electrical brakes were faulty, they may not have provided sufficient deceleration, allowing the escalator to overspeed. In addition to the motor and braking system, the escalator's mechanical components must also be scrutinized. The gears, chains, and rollers that drive the escalator steps are subject to wear and tear over time. If any of these components were worn, damaged, or improperly lubricated, they could have contributed to the incident. For example, a worn gear could have slipped, causing a sudden change in speed. A damaged chain could have broken, leading to a loss of traction. And improperly lubricated rollers could have increased friction, placing additional stress on the motor. The electrical system also warrants careful examination. A short circuit, a loose connection, or a voltage surge could have caused the motor to behave erratically. A short circuit could have created an imbalance in the motor's windings, leading to a loss of torque. A loose connection could have interrupted the flow of current to the motor, causing it to stall. And a voltage surge could have damaged the motor's insulation, leading to a breakdown of its electrical components. To comprehensively investigate the incident, investigators should conduct a thorough physical inspection of the escalator, paying close attention to the motor, braking system, mechanical components, and electrical system. They should also review the escalator's maintenance records, looking for any evidence of previous problems or repairs. Additionally, they should interview witnesses, including passengers who were on the escalator at the time of the incident, as well as maintenance personnel who have worked on the escalator. Finally, they should consult with experts in escalator safety and engineering to obtain their insights and recommendations. By combining all of this information, investigators should be able to develop a clear understanding of the causes of the incident and to recommend steps that can be taken to prevent similar incidents from occurring in the future. These steps could include improving escalator maintenance procedures, upgrading escalator safety features, providing better training for escalator operators, and increasing public awareness of escalator safety. To delve deeper into the potential causes of the Coors Field escalator malfunction, let's consider the concept of regenerative braking in induction motors, particularly in the context of a heavily loaded dam-running escalator. Regenerative braking occurs when the motor is driven by the load, effectively acting as a generator and feeding energy back into the power grid. This phenomenon is more pronounced when the load has a significant potential energy component, such as a heavily loaded escalator descending. In a typical induction motor, regenerative braking can lead to an increase in motor speed if not properly controlled. The motor, instead of consuming electrical energy, starts generating it due to the external force of the descending load. This generated energy can cause the motor to accelerate beyond its synchronous speed, potentially leading to a runaway condition. The escalator's control system is designed to counteract this regenerative effect, typically by using a combination of electrical and mechanical braking systems. The electrical braking system, often employing variable frequency drives or dynamic braking resistors, dissipates the excess energy generated by the motor. The mechanical braking system provides a fail-safe mechanism to stop the escalator in case of electrical system failure or overload. However, if the control system is not properly configured or if there is a malfunction in either the electrical or mechanical braking system, the regenerative braking effect can overwhelm the motor's ability to maintain a constant speed. This could result in the escalator accelerating uncontrollably, as hypothesized. Another factor to consider is the role of harmonics in the power supply. Harmonics are distortions in the sinusoidal waveform of the alternating current power supply. They can be caused by various factors, including nonlinear loads such as variable frequency drives, electronic devices, and even the induction motor itself. Harmonics can have detrimental effects on electrical equipment, including induction motors. They can cause increased heating, reduced efficiency, and even premature failure. In the context of the escalator, harmonics in the power supply could have interfered with the motor's control system, making it more difficult to regulate the speed and prevent the regenerative braking effect from causing acceleration. Furthermore, the escalator's step chain and drive system should be examined for any signs of wear or damage. The step chain is a critical component that connects the individual steps and transmits the driving force from the motor to the steps. If the chain is worn or stretched, it can cause the steps to move unevenly or jerkily, potentially leading to a loss of balance for passengers. Similarly, the drive system, which consists of gears, shafts, and bearings, must be properly lubricated and maintained to ensure smooth and efficient operation. Any signs of wear or damage in the drive system could indicate a potential for malfunction. Interaction between the escalator steps and the complaints at the landings is also crucial for passenger safety. The complaints are designed to mesh with the grooves on the steps, preventing passengers from getting their feet or clothing caught. If the complaints are damaged or misaligned, they can create a tripping hazard or cause injuries. Regular inspection and maintenance of the complaints are essential to ensure passenger safety. In addition to the technical aspects, human factors also play a significant role in escalator safety. Passengers need to be aware of the potential hazards associated with escalators and follow safety guidelines. These guidelines include holding the handrail facing forward and avoiding loose clothing or objects that could get caught in the escalator. Escalator operators also have a responsibility to monitor the escalator for any signs of malfunction and to take appropriate action if necessary. Proper training and procedures are essential for escalator operators to ensure passenger safety. By considering all of these factors, a comprehensive investigation can be conducted to determine the root cause of the Coors Field escalator malfunction and to implement measures to prevent similar incidents from occurring in the future. The investigation should involve a multidisciplinary team of engineers, safety experts, and human factors specialists. The team should collect and analyze data from various sources, including physical inspections, maintenance records, witness interviews, and power quality measurements. The team should also conduct simulations and modeling to understand the dynamic behavior of the escalator under different load conditions. The findings of the investigation should be used to develop recommendations for improving escalator design, maintenance, operation, and passenger safety. These recommendations should be implemented promptly and effectively to ensure that escalators remain a safe and reliable mode of transportation. It is important to note that escalator safety is an ongoing process that requires continuous monitoring, evaluation, and improvement. By learning from past incidents and implementing proactive measures, we can minimize the risk of future accidents and injuries.